Welcome to Practice Podcast number 86, and today we're looking at the Lattice Boltzmann Method again. We're going to continue from 85 podcast, which we looked at the first half of this paper. So if you haven't listened to that first half, or if you don't know what the Lattice Boltzmann Method is, check out that podcast, because in the first 10 minutes I go through a little bit briefly, but in fairly good detail, so you can understand what the Lattice Boltzmann Method for CFD is, how it's different to the Navier-Stokes set of equations, and it's very important, and it's going to be the next big thing in my opinion. So in that first podcast in 85, we talked about a couple different validations of the LBM CFD to Navier-Stokes CFD. And we're going to look at this, in this podcast, the third validation study, and also some Aeroacoustics. So to do that, we're going to look at this paper again. So application of a Lattice Boltzmann method to some challenges related to micro air vehicles. So and this is open access, so you can find it in the description. And one reason why micro air vehicles are so suited to the LBM at the moment is because the Lattice Boltzmann method is ideally suited to fairly low Reynolds numbers, mainly because of the limitations that it has in terms of turbulence and how much finer the grid has to be, and the lack of grid refinement ability at the moment, and also how the time step works with the actual grid itself, because they're implicitly coupled. So this is an ideal situation to look into. And as for the Aeroacoustics, this is very important as well. In a few weeks' time, I'm going to be doing another podcast with the Lattice Boltzmann method on Aeroacoustics for trains, and that's going to go into a lot more detail. But in this podcast, we're going to look into a little bit, and the reason why that's important is because traditionally the Navier-Stokes equations are the way that we implement them in practical situations, so URANs and even DES. The Navier-Stokes equations are terrible at predicting acoustics. So, for example, back maybe about 8 years ago or so, I have a friend who he was researching at the time noise coming from airfoils, and even with DES, he was having such a hard time just getting a basic, accurate noise spectrum from an airfoil with open foam DES. It wasn't matching experiments very well. He got the first, like the dipole quite well. The quadrupoles and the octopoles were well off. If you don't understand what they are, don't worry too much about them. Actually, you can listen to podcast number 23 and 24, I think, from memory. That those were ones on trains, and we're talking about noise on them. And I go through dipoles, quadrupoles, and octopoles in those, if you want to know more. But let's get into it now, and let's talk about this third validation case for the Lattice Boltzmann method. And this is the most complex so far. It's a three-bladed rotor optimized for aeroacoustic performance. And because it is so complex, they can't use DNS at the moment. They have to use an LES approach. And that just means, and that's because the Reynolds number is slightly higher and the geometry itself is slightly higher. So they say, whether for discretion in military operations or noise pollution in civilian use, noise reduction of MAVs is a goal to achieve. Aeroacoustic research has long been focusing on full-scale rotorcrafts. At MAV scales, however, the quantification of the numerous sources of noise is not straightforward, as a consequence of the relatively low Reynolds number that ranges typically from 1,000 to 100,000. Reducing the noise generated aerodynamically in this domain then remains an opaque topic. This part of the work deals with the numerical simulations performed through unsteady Reynolds average Navier-Stokes, or URANs, and the LES LBM, so large eddy simulation for the Lattice Boltzmann method, CFD, to study the flow phenomena that are responsible for the noise generation of a rotor in hover. So for the CFD setups, first of all, the LBM predictions are compared in this section with those provided by the URANs approach. The three-dimensional URANs equations are solved using a finite volume approach, which is standard, and they use the star CCM plus commercial code, which is a nice package. It's got a lot of functionality. I quite like it as well. I have a bit of experience with it. Now, for their CFD, this is a little bit interesting. They say that they used a K-epsilon model is employed for turbulence closure with maximum Y plus values below 1. So boundary layers are assumed fully turbulent. So that's good in terms of the Y plus values below 1. The K-epsilon model is like it's a piece of garbage. I'm just going to put it like that. I'm going to be blunt. It's not very good. But anyway, it is a very common turbulence model, and I don't recommend it. But anyway, that's what's often used. So let's talk about the geometry and grid convergence study, because this is important for the LBM. We'll discuss some of the details of it. So for the LBM, three grids are designed which all match all model LES requirements. So unlike the URAMs where they just needed one grid, I assume that they had validated this from other studies. With the LBM, they wanted to look at different grid resolutions. And the thing with the LBM method is that I mentioned in the first podcast number 85, is that when you discretize the domain, you pretty much have to do it just linearly. So it's all uniform. It doesn't mean it means that when you have very fine details, if you want to resolve those, if you want to effectively mesh them, it's not technically a mesh, but I'm just going to call it a mesh just to help you conceptualize. If you want to mesh them properly, you then need to make the entire domain that high resolution. Whereas for Navier-Stokes CFD, you can put in little regions where you resolve more finely, more detail. So that's the problem with LBMs at the moment, which is being solved in some packages. So anyway, with these three grids that they designed, the dimensions of the first cell in the direction normal to the wall is respectively set to 480 micrometers, then 35 micrometers, then 240 micrometers. And these corresponds to Y pluses of 35, 25, and 15. So it's well above 1. And as I mentioned, the reason why getting a Y plus of 1 is so difficult is because you need to have such a high resolution that the number of cells that you need just skyrockets. And they're designating these three different grid domains as grid 0, grid 1, and grid 2. The discretizations of the airfoil are thus, respectively, a delta x, so a distance of the cell size of 0.02 times the chord of the rotor, 0.015 times the chord, and 0.01 times the chord for the three grids respectively. So for the coarsest grid, the chord of the rotor will effectively split up into 50 parts. For grid 1, that will be split into 66.6666666666 recurring cells. And then for grid, the finest grid, it's split into 100 sections. So the radial direction from the root to the tip is then discretized into 183 points, 251 points, and 366 points respectively based on these three grid resolutions. To reduce the number of grid points, a hierarchical grid refinement approach is used with 7 grid levels. Okay, so they employed a grid refinement approach here, which must be custom because it wasn't in the package they used at this point in time, which was 2018. A grid level corresponds to a constant resolution part of the grid. The total number of points are respectively 23 million, 153 million, and 179 million for grid 0, 1, and 2. A full rotation of the rotor is discretized with 11,000 seconds, 11,000 time steps, 16,000 time steps, and 23,000 time steps for grid 0, 1, and 2. And this is again another thing to keep in mind when you're doing lattice Boltzmann methods, because the time step is implicitly coupled with the grid refinement. The more refined the grid becomes, the smaller the time step has to be. And so we then get like a huge number of time steps we need to just complete one rotation of the rotor. And this is why we see a reduction in the time step size as we increase the grid refinement. The influence of the mesh resolution is observed on the torque coefficient. And they plotted the effects of the grid resolution on the thrust coefficient and the torque coefficient in figure 8. And they say the results show that with all resolutions, the convergence of the torque coefficient is achieved after 4 rotations. So that's good. However, when you think about how many time steps you need to achieve 4 rotations, even for the coarsest grid, you need 46 million time steps. 46,000 time steps. That's a lot. For the finest grid, you need about 95,000 time steps. That's still a lot of many iterations. They say that, however, the torque coefficient is underpredicted by 10% with the coarsest grid compared to the finest grid, and by 1% with the middle grid to the coarsest grid. So once you hit the middle grid, you're effectively reaching mesh independence, or grid independence in this case. Despite the moderately good quality of the grid in the vicinity of the wall, the torque coefficient is not sensitive to the grid resolution when considering a resolution higher or equal to the distance of the cell being 0.015. So I mentioned that the rotor was split up into 66.66666666 recurring points. When you've reached that level of resolution, then the torque becomes insensitive to any higher. So that's good. They say only data obtained with grid 1, this grid, for which torque and thrust coefficients are converged, are analyzed for the rest of this paper. And you can see with the torque of these results, the grid 1 and grid 2 mimic each other very nicely, even from the very start when you're just ramping up the simulation. They're mimicking each other very well, whereas the courses grid is a little bit off entirely. So for grid, for comparison with the measurements, so they want to now, we've done a grid resolution study, now we're looking at how the results compare with URANS and another CFD approach, or numerical approach, called BEMT. And this BEMT method, BEMT, is designed specifically for rotors, so it's specialized. In figure 9, they have the comparison of the global performance, thrust coefficient, and torque coefficients for these 3 different approaches. And they say that at 3000 RPM, the accuracy of the LBM on thrust is very good, about 1% off compared to the measurements. Both URANS and BEMT overpredict the thrust coefficient by 15%. So even BEMT, which is designed specifically for rotors, is off a little bit. When considering the torque coefficient, the order of the methods regarding the accuracy is inverted though. So the LBM, URANS, and BEMT overpredict the torque by 50%, 40%, and 21% respectively. That's horrendous. At 49,500 RPM, similar conclusions can be drawn. The thrust coefficient is underpredicted by 2.5% by the LBM method, but still overpredicted by the URANS and BEMT methods by 14 and 17% respectively. So in other words, pretty much at any RPM, effectively, the LBM approach quite accurately predicts the thrust coefficient, whereas the BEMT and URANS approaches do not. However, for the torque coefficient, none of these approaches accurately predict the torque coefficient, but some are better than others. They say that at a RPM of 4,950, the LBM, URANS, and BEMT overpredict the torque coefficient by 29%, 23%, and 12% respectively, so it's getting better. It is unclear why 3 very different numerical methods overpredict the torque, especially the BEMT, which neglect 3-dimensional effects and predicts fully attached boundary layers. Unfortunately, due to the lack of experimental data, it is not possible at this moment to identify the origin of such discrepancies. So this shows you how, even though we think that our equations are good and our setups are good, we can get very different results. And it could be due to the equations that we use, or it could be due to the setups. Maybe the time steps weren't fine enough. I don't know. Maybe more information needs to be done about that, or even the turbulence modeling, the equations used there, because LBMs use turbulence modeling as well, depending on the situation. So in figure 10, it shows the comparison of the local thrust coefficient along the rotor span for the LBM, URANS, and BEMT approaches. The main conclusion is that the 3 numerical methods agree reasonably well on a large part of the rotor span, but predict very different behavior close to the tip due to 3-dimensional flow effects, and we'll see this a little bit later as well. And 3-dimensional flow effects are due to pressure differences and even separation patterns. So it's understandable that if they are going to introduce errors, this is where it's going to happen. Whereas with the root and the rest of the wing, it's usually a lot more simple flow going on there. Now let's talk about the analysis of the blade vortex interaction. One of the dominant sources of noise, so now we're going into the noise part for this rotor, is the present rotor comes from the ingestion of turbulence by the leading edge of the rotor blade. So in other words, when you have a rotor going around, one blade ahead, there's obviously some turbulence coming off of that. When the other blade behind comes and sweeps through it, this then starts chopping up all this turbulence, and you start getting a lot of noise. And depending on whether the structure upstream that is chopping through is coherent or not, will depend whether you get coherent noise or incoherence. In other words, whether you get tonal noise or broadband noise. In other words, if you have a wingtip vortex, for example, this is coherent. It's always happening. And when you have the blade going through it, you're constantly chopping the exact same phenomenon at the exact same frequency. So you're going to be getting tonal noise. Whereas if you have just general turbulence coming off of a blade and you chop through that, you're not really getting a consistent phenomenon happening. So there's no real consistent frequency, which means that you're going to be getting more of a broadband noise. So this is just what this means. And in figure 11, this shows the instantaneous isosurfaces of the Q criterion colored by the pressure coefficient. And this shows that there is a lot of turbulence coming from the blades, from the wingtips particularly. And they say that 3 different vortices are generated close to the rotor tip. One starts at the leading edge, one comes from the pressure side, and one begins at the midchord. So the midchord one might be due to, I think that's probably due to the roll up from high pressure to low pressure, because that's often what happens with airplane wingtips as well. That's where like you can start seeing it happen. But if you know any more about this, let me know as well in the comments below. So the breakdown of these 3 vortices start close to the trailing edge due to the recompression. These vortices merge also with the vortex due to the separation of the suction side boundary layer close to the tip. The mixing process between the different vortices produces turbulence that impacts the following blade, located in the left part of the figure. So we can see it here. Now, one thing, from what I can tell, all these vortices are of the same sign, so they're rotating in the same way, and this means that they are not annihilating each other. They can be constructively interfering with each other potentially. So that can lead to more noise potentially. In figure 12, they show the time average flow field colored with the normalized streamwise component of velocity for the URANS and LBM methods. And they look very similar. There are just some differences in the, let me zoom out a little bit so you can see both of them at the same time. And by the way, if you're listening to this, you can also see the video on our YouTube channel, or you can just download the paper in the link in the description, or just listen and I'll describe it to you as well. So the streamwise component of velocity for both of these 2 methods, URANS and LBM, are very similar up until the wingtip. Then we start to get a little bit of a difference downstream of the wingtip, and that's probably due to the vortices, how they break down. They say that the similar flow patterns are observed between these 2 flow fields, such as the contraction of the wake. Most of the thrust is achieved in the external part of the rotor at a radius greater than 0.5. So in other words, the outside half of the blades. However, as expected, some discrepancies appear close to the tip. In the case of the LBM, a boundary layer separation is observed on the suction side of the blade, and the tip vortex has a low influence on the flow at this location. On the URANS flow field, though, the influence of the tip vortex is well highlighted, and its influence on the velocity field is observed even far downstream of the blade. So in other words, these vortices persist further downstream. And this is probably due to potentially turbulence modeling, the model that they had adopted compared to the LBM method. That could well account for the differences in the vortex breakdowns. So moving on to figure 13, now we're looking at the wingtip section a little bit. So figure 13, the time average flow field colored with the vorticity magnitude downstream of the trailing edge for the URANS and the LBMs are shown. So in other words, they're highlighting where the vortices are. To point out the influence of vortical flows in this configuration, a flow field is extracted at 50% of the chord downstream of the trailing edge and colored with the normalized vorticity magnitude. So in other words, you have the rotor tip, the trailing edge, you go downstream about 50% of the chord, and we take a slice through there. So the wake generated downstream of the blade is then convected by the flow in a streamwise direction, with a higher speed in the vicinity of near the wingtip effectively. In the case of the Lattice Boltzmann method, a region of intense vorticity is also observed in the tip region, corresponding to the merging of the vorticity generated by the tip vortex and the boundary layer separation. So we don't see that with the URANS situation here. The effect of the tip vortex generated by the previous blade is also visible as a diffuse flow pattern, rather than a coherent vortex, which we see with the URANS situation. So in other words, as we mentioned, the breakdown of the wingtip or the vortices downstream of the wingtip section persist not as strong for the URANS situation. So in other words, they persist downstream longer than for the LBM situation, and we see this here. This observation, is compatible with the flow dynamics already reported in Figure 2, however, at a much lower Reynolds number. On the contrary, in the case of URANS, Only one very intense vorticity region is observed in the tip region, corresponding to a coherent vortex, whereas for the LBM method, we had the tip vortex plus the separation vortex from the boundary layer that we see. They're kind of merging together or mixing together a little bit. The trace of the previous vortex, which is still coherent, is also visible below the rotor trailing edge. The conclusion at this step is that the performance discrepancy between the LBM and the URANS comes from the discrepancy of the behavior in the tip vortex, so the breakdown in the case of the LBM, and the prediction of the boundary layer separation on the suction side, close to the tip in the case of the LBM. So this could be due to a whole number of factors. It could be due to the turbulence modeling. It could be due to the grid resolution. So again, as I mentioned before, the Y plus for the LBM was not 1, it wasn't below 1, whereas the URANS was. The minimum Y plus was, I think, 15, and then it went up from there. That could very well change the boundary layer development in the CFD very easily. It could be that. It could also be just the turbulence modeling that they use. It could be the time steps. It could be a bunch of different things. So regarding the prediction of acoustic emissions, the question of potential tip vortex breakdown is of major importance. As shown in figure 13, in the case of vortex breakdown, the turbulence generated by the tip vortex can impact the following blade on a large part of the span, which is not the case if the vortex remains coherent. So in other words, in this situation where we saw the vortex coming from an upstream blade still persisting well downstream for the URANS, if that impacts another blade, that's going to create noise. So that means for the URAN situation, there is more potential for there to be noise, whereas for the LBM method, there's less potential. There's potential for that because this vortex is already broken down by the time it's reaching another blade. So that's where the noise prediction could be very different. So in figure 16, we now look at the effects of different designs on acoustic performance. They're using now the LBM method just to look at general aeroacoustics, and they're using a general understanding of a flow control device, which is near and dear to my heart. I'll get to in a second. And we know how this flow control device affects noise production of rotors and wings in general. And they're seeing if the LBM method also picks this up. So the effect of different designs on acoustic performance. 4 designs are investigated with the objective to reduce the blade-vortex interaction and thus to increase the acoustic performance. The original geometry is referred to as the reference. The second geometry, referred to as wavy, is the reference geometry, which includes tubicles at the leading edge. So tubicles are a really cool flow control device, which I've done a lot of research on, and they're effectively just bumps on the leading edge of an airfoil. And the way that they work is very similar to a vortex generator, the difference being that vortex generators typically located about 25% chord downstream of the leading edge, which means that this is where the vortices are being produced. Tubicles are on the leading edge, so that you're getting vorticity being produced at this point and it's going over the entire wing. It's a slightly different topology going on, but often they achieve the same results. So those are tubicles, and they can be characterized by their wavelength, so how much they're squashed together, and then how the amplitude, so how much they poke out. And for this one, they say the wavelength of the sinusoidal variation is 0.28, which I don't know what they're referencing here, because the typical notation for tubicles is A for amplitude and lambda for wavelength. But from what I can tell just from this figure, the wavelength of a tubicle is about 30% of the core of the span. They say that the amplitude is 0.05, so I'm guessing again 0.05 of the span, I think. So they're fairly large, and fairly large tubicles typically create a softer and more gentle stall pattern. So why are we using tubicles for acoustic control? Let's get into that. The use of tubicles at the leading edge is a promising way to increase the aerodynamic and acoustic performance of profiles. However, it has been poorly investigated for rotating profiles. The third geometry, referred as shifted, is the same as the reference geometry, except that the 2 blades are shifted along the z-axis. The second blade is shifted by a z on r, so in the z-axis compared to the span of minus 0.057 below its initial position, and the third one is shifted to 0.057 above. So in other words, they're just like One's at the same height, one's pushed a little bit lower, one's pushed a bit higher. We're getting back to tubicles. They, for noise, they are very good at reducing tonal noise depending on the tone, but there's a lot of potential for them there. And they've been investigated for fans a lot and for general airfoils. So they're very effective. And actually, I know the person who first discovered this, and she found this out by when she was testing in the wind tunnel. Apparently, because she was testing for long hours, and she noticed that when she was testing the typical airfoils, they're quieter. So she wanted to then test them out, and you can see her papers. Her name is Christy Hansen, and she also did this about 10 years ago. So you can look up those papers if you like and see for yourself. I might do some podcasts on them in the future as well. So let's get back to this LBM situation here. For the three designs, a breakdown of the tip vortex starts close to the trailing edge. A time average flow field obtained in the reference frame of the rotor and colored with the normalized fluctuations of pressure is shown in figure 16. So we can see here the figure 16. And why this is important is because the fluctuations in pressure are what determine the noise. So for the three designs, most of the pressure fluctuations are observed at the two locations close to the trailing edge in the vicinity of the rotor tip, so tip vortex and the suction side. So in other words, most of the noise is coming from the wingtip section, which we know about, and the trailing edge, which is quite normal. The noticeable differences between the three geometries are: one, for the reference and the wavy leading edge cases, the three blades exhibit the same field of pressure fluctuations, but it is not the case for the shifted blades. That's because the shifted blades are not like sweeping through the wakes of the other blades ahead of it, as much at least. The second difference is the source of the fluctuations at the tip rotor, the rotor tip, is reduced by the wavy leading edge, which is very expected. We've seen this before. One potential reason why, I'm not sure, I haven't investigated this particular bit, but I know about how tubicles work. And one potential reason why this is because it's counteracting the circulation being produced over the airfoil and the wingtip vortex. So you can reduce the noise at the wingtip, I think, with this mechanism. Again, I haven't investigated this, so I'm not going to say for sure, but I think that's what's going on here. The third difference is the level of pressure fluctuations in the shifted blade geometry is reduced for two blades, the top shifted and the middle blade, and is increased for the last blade. Compared to the reference geometry, the shifted blade reduces pressure fluctuations at the leading edge, but it has detrimental impacts on the trailing edge noise. The global noise of each configuration can be evaluated at a distance of 10 rotor radii downstream by integrating the pressure signals on all frequencies, which gives a total noise of, for the reference case, of 64.9 decibels, for the tubical case or wavy leading edge case, 64.1 decibels, and for the shifted case, 68.4 decibels. So in other words, we can see here that the LBM method works pretty well because it predicted that the tubical rotor should reduce noise by a little bit, which it does. So it has picked up this phenomenon quite well. The magnitude hasn't been investigated, but that's for another day. So the aerodynamic performance is plotted in figure 17 with respect to the acoustic performance. So this shows a figure of merit comparison between all these airfoils. And they say a validation of these results can be found in Sarah and others. This analysis of the LBM results demonstrates that the adaptation of the leading edge is a potential solution to increase both the aerodynamic and acoustic performance of MOV propellers, which agrees very well with literature. So the LBM method has picked this up. So that's in this podcast and the LBM method section at the moment. I'm going to be doing more Lattice Boltzmann podcasts in the future because it's really cool. Let me know what you think about Lattice Boltzmann and Navier-Stokes CFDs, and if you have any experience with Lattice Boltzmann, etc. And make sure to like and subscribe. This helps us out a lot. And tell your friends as well, because if you're doing any aerodynamics, you want to know about Lattice Boltzmann, and they should check out this podcast and podcast number 85. And also, if you want to get better at CFD yourself, check out our courses, link in the description, and we do theory there as well. And I'll see you in the next podcast. Peace out, amigos.